everybody. In this video, we're going to talk about how to convert between fractions and decimals and how to teach your students how to convert between fractions and decimals. So the first thing we're going to look at is how to convert fractions to decimals. So there's two different methods you can use. One is called the prime factorization method and the other is long division. So, the way that the prime factorization method works is you find the prime factors of the denominator of whatever fraction you're trying to convert to a decimal. So, I would say, okay, 4 can be factored into 2 times 2, and 2 is a prime number. So, that means my prime factorization is done. And I just write that 4 equals 2 times 2. Now, the idea behind the prime factorization method is that decimals are basically just special fractions that have denominators with powers of 10. And so if I have a denominator of a fraction that is 2 times 2, well, 10 is 2 times 5. So I could convert this fraction into a fraction that has a denominator with a power of 10 by multiplying by 5 times 5. Because this 2 times 5 would make 10, and this 2 times 5 would make 10. And so if I multiply the bottom of my fraction by 5 times 5, I'll make a fraction that has a power of 10 in the denominator. Now, if I multiply the bottom of a fraction, I also need to multiply the top of the fraction by the same number to make it an equivalent fraction. And when I do that, the top of the fraction is going to be 5 times 5, which is 25, times 3, which is 75. So I'll get 75 over 2 tens multiplied together because the 2 times 5 makes a 10, and I have two pairs of those. So I get 75 hundredths, and then I can convert this into a decimal because 75 hundredths would be 0.75, where the 5 is in the hundredths place because the last digit of whatever's in your numerator needs to be in the last place value that's determined by the denominator of that special fraction with a power of 10. So that's how you would use the prime factorization method. The other method is to do long division. Because remember, we talked about in our equal sharing videos that if you have the fraction 3/4, an easy way for students to think about this is that you have three whole pizzas or pies or whatever you want to do that are being split equally between four people. And each person ends up with 3/4 of a pizza or of a pie or whatever. And so if I want to convert this fraction into a decimal, I'm going to divide 3 by 4 and use long division to find my decimal. So the way I would do this is I would say, okay, if I have three whole things and I want to divide them into four equal groups, I obviously can't do that because I only have three of them. So I'm going to put 0 wholes in each group. And then I'm going to take those three wholes and I'm going to convert them into tenths because that's my next place value. And I'll have 30 tenths. And when I divide those into four equal groups, I have enough to put 7 into each group. And when I put 7 tenths into all of my four groups, I end up with 28 tenths in each group. And I can subtract that, and that tells me that I have 2 tenths left over. Well, I can take those 2 tenths and convert them to the next place value, and that gives me 20 hundredths. And if I divide 20 hundredths into four groups, I get 5 hundredths in each group. And that takes care of all 20 of my hundredths, so I have a remainder of 0. And once you have a remainder of 0, that tells you that long division is done. And so the equivalent decimal would be 0.75. So that's how you can convert fractions to decimals. And the prime factorization method only works if the denominator of your fraction factors into prime factors that include 2s or 5s. Because 2 times 5 equals 10. But if you have a factor like 3 or 7 or 11 or something like that, those numbers, you can't multiply them by anything to make them equal 10, or at least not any whole number. Technically, there are some fractions you could multiply by, but you can't multiply them by any whole number to get the number 10. So let's do another example of this. So if you have the fraction 9/40 and you want to use the prime factorization method, The prime factorization method will work in this case because if I say, oh, 40 is 4 times 10, 4 is 2 times 2, those are prime numbers. 10 is 2 times 5, and those are also prime numbers. You get this prime factorization, and because it only involves 2s and 5s, then you're good to go. And so you can say, okay, well, I already have one pair of 2 times 5 in my denominator that makes a 10. But the things that I'm missing are 2 more 5s to pair with these 2s to make the number 10 in the denominator. So I'm going to multiply the top and the bottom of my fraction by 2 5s. And when I multiply the top of the fraction by my 2 5s, I get 5 times 5 is 25 times 9, I think is 225. I'm thinking about that right. And then in the bottom of my fraction, I have 3 5s or excuse me, 3 10s multiplied together because I have 3 pairs of 2 times 5. So I'll have 1,000 in my denominator, which means that 9/40 equals 0.225 because the 5 is in the thousandth place value. So that's how I would do this with prime factorization. And like we were talking about, some fractions won't work when you do their prime factorization. Because if I try to factor out 6, 6 is 2 times 3. And I could do 2 times 5 to make 10, but there's no whole number I could multiply 3 by to get the number 10. And so the prime factorization method won't work in this case. So instead, I'll do the long division method and I'll think about it as 1 divided by 6. If I have one whole, trying to split it into 6 groups won't work because I only have one whole. So I'll put 0 wholes in each group and convert that one whole into 10 tenths. When I take my 10 tenths, split it equally into 6 groups, I get 1 tenth in each group. And that 1 tenth in each of the 6 groups takes care of dividing 6 of my tenths, which means that I have 4 tenths left to divide. When I convert those 4 tenths into hundredths, I get 40 hundredths. 40 hundredths, if I split those into 6 groups, I have 6 hundredths in each group. And that takes care of dividing out 36 of my hundredths because each of the 6 groups got 6 hundredths. And I have 4 hundredths left to divide. By the way, this is kind of just a little tangent. We'll be going into more detail of how to teach long division with decimals to your students in a later week. So I'm going through this really quickly, but we will go into more detail of how to explain this visually to your students so they really understand it. So anyway, I have 4 hundredths remaining, so I'll convert those 4 hundredths into thousandths, and I have 40 thousandths. 40 thousandths split equally into 6 groups gives me 6 thousandths in each group, which uses up 36 of my thousandths, and I have 4 thousandths remaining. Now, you might notice that this little pattern right here is repeating itself over and over because I keep getting a remainder of 4. And so what this means is that this decimal is actually going to go on forever because I will continually get a remainder of 4 over and over and over and over and over again, and this pattern will repeat itself. So this is what we call a repeating fraction, or sorry, a repeating decimal. And the fraction 1/6 is equal to the decimal 0.16, and we write it with a bar over it that's called a vinculum to show that that digit repeats itself over and over and over. And actually, most fractions will be repeating decimals when you convert them to decimal form, because the only fractions that don't end up as repeating decimals are the ones where you have prime factors of 2 or 5. So any decimal, if you factor any fraction, if you factor the denominator and you get something other than 2 and 5, then it will make a repeating decimal. So, and there's also lots of different types of repeating decimals. So we did one where we just had one digit repeating, but you can also have multiple digits repeating. Like for example, if you do 2 divided by 7 in your calculator, the decimal you'll get is 0.285714, 285714, 285714, 285714. And that sequence of numbers will repeat itself over and over. And some bigger fractions will have even bigger parts that repeat themselves over and over, like this one. And there are some decimals that go on infinitely long that don't repeat, but those decimals cannot be written as fractions. A really common example of this is the number pi. Pi is an irrational number, which means that it cannot be written as a fraction, where the numerator and denominator are whole numbers. Technically, it can be written as a fraction because it's the circumference divided by the diameter, but one of those will not be a whole number. And so it's not the definition of a rational number. So we have repeating decimals, and most fractions, when you convert them, will turn into repeating decimals. But some of them will not if the denominator of the fraction can be factored into twos or fives. So now let's talk about how we can convert decimals to fractions. So if we have some decimals like this, the way that you can convert the decimal to a fraction is you basically just look at the last digit of the decimal. If it's a terminating decimal, which these two are, um, we look at the last digit and we say, okay, what place value is that? Well, that's the thousandths place value. So we're going to put 1,000 in our denominator. And then in the numerator, we'll put the number 581 because those are the digits that come before our last digit in the decimal. Now, the reason why this little trick works is because of what the place values mean. So the 5 is in the tenths place, which means we can write it as 5/10. The 8 is in the hundredths place, which means we can write it as 8/100. And the 1 is in the thousandths place because it's in the thousandths place. So we can write it like that. And we talked about this a little bit, but I just want to review it again. Um, if you add all of these place values together when they're in expanded form, when you add fractions, you need to have common denominators. And so to make 5/10 have a common denominator of 1,000, I would need to multiply the top and the bottom by 100, which would give me the equivalent fraction of 500 thousandths. And 800ths would be written as 80 thousandths. And once you have common denominators, you can add them all together, and you do get the number 581 in the numerator. And this will always happen regardless of what the decimal is. And so this process of looking for the last digit basically just tells you what the common denominator will be because this last digit was in the thousandths place value. And then all of the digits before that will just be written in order in the numerator because of the way that the decimal system works. So that's how you do that one. If we do 2.34 and we try to write that as a decimal, the 4 is in the hundredths place. So we'll put 100 in the denominator. And then we'll write 234 in the numerator. And this makes sense because the decimal 2.34 is greater than 1. And the fraction 234 hundredths is an improper fraction, which is also greater than 1. And this one we could actually reduce because the top and the bottom are divisible by 2. So if we divide the bottom by 2, we get 50. If we divide the top by 4, we're going to get 117. 50, I think, can only be divided by 2 and 10. I think those are the only prime factors, which also makes sense because this was a terminating decimal. And 117 can't be divided by 2 or 5. So this is our fully reduced fraction there. Okay, so this is how you can convert terminating decimals into fractions. But let's talk about how we can write repeating decimals as fractions. So this actually requires a pretty good amount of algebraic thinking. And by the time you are ready to teach this to your students won't have done a lot of algebra. And so you want to kind of scaffold their algebraic thinking in the way that you discuss this with them. So you might say, okay, first of all, what does an equal sign mean? You know, like if I have an equal sign, what are some things I could put on both sides of this equal sign that would make true math sentences? And they might say things like, oh, 1 plus 2 equals 3, or 7 minus 5 equals 2, or 3 times 4 equals 12. And you can say, yeah, those are all true statements. They all um, are accurate uses of an equal sign. And then you could say, so what about if I had something like this? Is this a true statement? If I had just two numbers equal to each other, is this true? And they, at this point, they would have done a lot of work with fractions and decimals, and this is one of the easiest fractions and decimals that we have. And so they say, yes, this is true. 1/2 is equal to 0.5. Those two numbers are equal to each other. And so you'd say, okay, well, since we want to find out what fraction 0.32323232 is, why don't we just write an equation that describes what we're trying to find? So we don't know what this fraction is yet. That's what we're trying to figure out. But let's give it a name. So I'm going to name this fraction f for fraction. And I'm going to say, whatever this fraction is, this equals the decimal 32323232, etc. And I'd say, okay, cool. So I have this fraction. I have the decimal that it's equal to. And one of the concepts of equal signs is that I can do the same thing to both sides of the equal sign, and it won't change the trueness of the math statement. So, for example, if I have 2 plus 3 equals 5, if I add 1 to both sides of the equation, is it still true? Yeah. It's the numbers have changed because now we have 6 equals 6, but it's still a true statement. Um, and the trueness of it hasn't changed. And then you could say, okay, what if we had a really easy equation like 4 equals 4? If I multiply both sides of the equation by the same thing, is that still true? And they'd say, yeah, that's still true. If you multiply both sides by the same thing, it's equal. And so you'd say, okay, well, what happens if I do 10 times f? What does that equal? And your students might say something like, well, we don't know what that equals because we don't even know what f is. And you could say, yeah, we don't know what f is. However, we do know that f is equal to this big long decimal. And if it's equal to that big long decimal, then 10 times f would have to be equal to 10 times that decimal. And what is 10 times that decimal? And if they've had a lot of experience multiplying decimals by 10, it would be pretty easy for them to say that this is going to be 3.232323, etc. You'd say, great job. Okay, so what would 100 times f be? Even though we don't know what the fraction is, even though we don't know what f is, what would 100 times it be? And they would end up with 32.323232, etc. And you'd say, okay, cool. So I have the mysterious fraction that we don't know, but we called f, is equal to the decimal point 32323232. 10 times that mysterious fraction is equal to 3.232323. 100 times the mysterious fraction is 32.323232. And then I'd say, okay, what if I took this number and I subtracted this number? So I'm just going to write that right here. If I subtracted 0.323232, etc., forever, what would happen if I subtracted those? And because the decimals match each other exactly, when you subtract them, you would get the number 32. And you'd say, okay, well, that seems really useful because basically that got rid of all of the repeating decimals, and now I just have a whole number. And we know from our examples over here that if I add something to both sides, the equation stays the same. If I multiply something, it stays the same. And it makes sense that it would also work if you subtract something, because if I had, I don't know, 11 equals 11, if I subtract 5 from both sides, that's still going to be a true statement. And so it seems reasonable that we could subtract this decimal from the 32.323232, and as long as we also subtract it from the other side. However, this is going to be really messy because I don't even know what f is. So I definitely don't know what 100f is. And that would be really difficult to take a mysterious fraction times 100 and subtract this decimal that goes on forever. But it is not very hard if you remember that this mysterious fraction, or sorry, this really long decimal is equal to the mysterious fraction. So we don't necessarily have to subtract this huge long decimal. We could just subtract our mysterious fraction, which is way easier because 100 times f is f plus f plus f plus f plus f plus f 100 times. Now, usually we don't do it that way because it takes forever to add 100 f's or 100 fractions together. But in this case, it would be easier to think about it that way because if you have 100 f's added together and then you subtract an f, how many f's do you have? Well, you just have 99 Fs or 99 fractions. Sorry, I'm switching into my middle school teaching mode. You would want to say fractions instead of Fs every time I'm saying this. So you'd say, okay, you have 99 fractions of this mysterious fraction we're looking for added together, which we could write as 99 times that mysterious fraction. And then once you have this statement, you're almost done because you don't have a repeating decimal anymore. And you know that 99 times your fraction is going to equal 32. And some of your students might be able to find the answer just from this, depending on how much practice they've done with multiplying and dividing fractions. But even if they don't, you can say, okay, so we know that 99 times our mysterious fraction equals 32. And could we use our multiplication and division fact families to write an equation where f equals something that has to do with 32 and 99? And because division is the inverse of multiplication, you could use your fact families to write this as 32 divided by 99. And remember that fractions are basically just another way to think about division because the fraction, let's say like 1/2, this is equal to one piece of pizza divided equally between two people. And so if I have my mysterious fraction equals 32 divided by 99, well, that just tells me that my mysterious fraction equals 32 99ths. And now I know what my mysterious fraction is. And you could have your students double check this by doing long division with 32 99ths to make sure it really does turn into this decimal. But that's the process of converting a repeating decimal to a fraction. So I'm going to do one more quick example. I won't go quite as much into the scaffolding of how you teach this to your students, but I want to do just one more quick example so you can see the process. So if I have this decimal that is 0.416666666666 repeating forever, the way that I would want to convert this into a fraction is I would say, okay, I'm looking for the fraction that this is equal to. If I multiply that fraction times 10, I would get 4.1666666. If I did 100 times this fraction, I would get 41.666666. And if I did 1,000 times this fraction, I would get 416.666666. And when I look at all of these numbers, it looks like the ones that I should subtract to get rid of my repeating decimal are these two. Because if I were to take this number and subtract this number, it would get rid of the repeating decimal, but I would still have something left in the decimal place because the 66 hundredths would be subtracting 41 hundredths. And so you would still have a decimal. Technically, it would still work, but it would make it a little harder. So it's easiest if we subtract the decimals. That will get rid of all of the decimals as well as the repeating part of the decimal. So I'm going to subtract 41.66666666 from 416.666666. And when I do that, I get the whole number 375 because all of the decimal stuff cancels itself out and 416 minus 41 equals 375. Now, what is this equal to? So I subtracted 41.66666 from one side of my equation, which means I also have to subtract it from the other side of the equation. However, it would be easier if rather than subtracting this infinitely long decimal, I subtracted 100 F's that are added together. So I'm going to subtract 100 times F. And if I have 1,000 F's added together and I subtract 100 F's added together, that's going to give me 990 F's or this mysterious fraction. So once I've got this, then I can use my fact families to say F, or my mysterious fraction, equals 375 divided by 990. And because fractions are another way of thinking about division, I can write this as 375 over 990. And then I can just go ahead and reduce this. So if I divide the top and bottom of this fraction by 5, 375 divided by 5, I think, is 75. And 990 divided by 5 is 198. I know that 75 is divisible by 3 and 25. 198 is not divisible by 25 because you can't divide by 5 even. But I think it might be divisible by 3. So let's divide 193 by 3. And when I do that, I get 66. So when I reduce this, I get 25 over 66. And that's fully reduced. And so it looks like 0.41666666 is equal to 25/66. So I hope that was helpful. If you have any questions, let me know. And I hope you have a great day.